All right, everybody. I hope you're feeling refreshed and caffeinated. We're going to start this session maybe a few minutes late, but that's okay. The mission will be on time. We don't have to be. So this is the session on binaries and multi-messenger science. I'm Tyson Littenberg from NASA Marshall, who will be your chair for the session. Our first talk is one that is remote. It'll be Cezar Ionescu from the Institute of Space Science. Do we have, yep, there we go. So Cezar, can you hear us all right? Can we hear you?
Yes.
There you are. Okay. We are ready when you are. Take it away.
Okay, 1 second. What's this? Great. It works perfect. So, hello everyone. I'm Cezar. I'm from the Institute of Space Science from Romania. And today I'm going to present to you when can two nearby LISA sources look like one source. We will explore the extrinsic geometry, the waveform manifold, and zones of confusions. So, firstly, we will like to address why this is an important question. Due to the fact that LISA data will be intrinsically multi-signal, the issue will not be about the sensitivity, like noise, the signal-to-noise ratio, but mostly about the degeneracy. And the simplest case that we can solve is one with two sources that can be approximated by one effective source. And how can we do this? And why should we do this more precisely? Well, we are expected that the LISA data will intrinsically be multi-source signal, and many sources are expected to be overlapping in the frequency, in the time and frequency. So the analysis must be therefore global rather than event by event. We can make a rough estimate that in 4 years we will see somewhere along the lines at 10 to the power 7 galactic binaries, and most of them will not be single source, but or not easily separated from the bulk of the data. Therefore, from just a rough estimate, we can, assuming Poisson distribution of the number of galactic binaries on the number of bins, we can say that at least 70% of the data will be undistinguishable. Like we cannot distinguish a single source, two sources, three sources, five sources. It will be hard to distinguish this in the waveform domain. Therefore, what we propose from a geometric standpoint. We will start from the geometric preliminary. We define the Hilbert standard noise-weighted inner product. This is the standard stuff. And a single source model will be embedded, a waveform that is embedded in a manifold in the Hilbert space. As we can see right here, a single source can be represented as a manifold. And for a two-source signal that live in the two-source manifold, we assume it's a superposition of single sources, of two single sources. We want to discern from the two sources, from the one source from the two sources, or the two sources from the one source. For a waveform, for a waveform data that is from the two sources, we can define the distance from the two source to the effective one source as like this. And we will try to minimize this function so that we have the least amount of confusion in the data. Because we assume Gaussian maximum likelihood, we have the common and well-known relationships, and we get the final relation of 1/2 the distance squared. Now, usually when we talk about formulation in metric spaces or in manifolds of parameter spaces, we use the Fisher matrix or the Fisher metric. But in this case, this will not be enough due to the fact that this is no longer a problem of local motion along a single source manifold, but rather the source of confusion comes from the projection problem, from the two-source manifold to the nearest point on the one-source manifold. Therefore, doing this, we'll have the best fit problem given by this equation. This equation will give the following geometric meaning. The optimized residual that remains when we vary the theta parameter is normal to the M1 manifold. So the leading irreducible mismatch is therefore the extrinsic curvature of the M1 manifold. And we shall see as such that in our main local result is that for two equal amplitude sources, we have the following formula. And this small data is a small displacement in parameter space. When we try to minimize the function that I showed earlier here, we'll not go over the derivation. The only residual that remains is the second fundamental form, that is basically the second derivative, but only the normal component of the second derivative. If we vary the theta parameter in M1, in the single source manifold, we can get rid of the linear components, but not the second component. Therefore, the only components that survive this projection are the second fundamental form. And if then we go to the distance squared that we talked about earlier, we see that it's characterized by the amplitude squared over 16 and the modulus squared of the second fundamental form in a general direction. For if we are talking about unequal amplitudes, we can define then an effective amplitude as such, and therefore the formula remains pretty much the same. But in place of the general amplitude, we have the effective amplitude. This is not any different. It gives the same results, but in the easiest case is the one with equal amplitudes. Given this threshold of the distance, we can define a minimum radius or a minimum direction in which we can conjure confusion maps. This distance is model agnostic. This can be put in by depending on our interest in the data. It's not something that can be derived. It's just something that can be later like a free parameter. For our numeric implementation to see if the theory holds up, we test this pipeline using 6 parameters in frequency domain in spiral mode. And as such, we have the amplitude, the chirp mass, the coalescence time, the coalescence phase, and 2 spins. We use spin orbit coupling and inject the subdomain of 3-3 harmonics, not only the quadrupole approximation. We then go with this and into the time delay interferometry projection into the AET channels. Then, this is standard stuff, then we do the automatic differentiation for tangent vectors and directional Hessians. So we can do actually the calculations of the distance. And we do the low memory BFGS optimizations for the direct speed validation. This is usually just to not solicit so much the PC due to high memory demands of the Haitians. For a direct validation, we used the numerical optimization of the theory versus the predicted theoretical model. We have on the x-axis the parameter separation that we said, the deltas, and on the y-axis the distance. We can see right here that about 10 to the minus 17 that the data does not follow anymore the line. This is due to memory loss, so it's a numerical artifact. This is not something that has to do with the theory being wrong at lower distances, but we simply do not have enough bins to derive the data lower on the axis. So the theory holds up pretty well on this, just testing it on all dimensions. So this was tested on all 6 parameters that we saw here. And that's all fine, but what are the use cases for this? The use cases would be confusion maps. So we are trying to see, okay, how do we separate the 2 sources from just an effective 1 source? And we go now with pairs of different parameters. So for instance, we have the chirp mass and the coalescence time. And we see that this blue zone here is the confusion zone. Like if our data separation is in this blue zone, we can no longer make claims, very strong claims about if it's a 2 source or a 1 source. It could very well be a 2 source or a 1 source that produces the wave packet that we saw. We can also see from this graph that the coalescence time is much more sensitive. In the geometric formulation that we talked earlier, we can interpret this as having a higher extrinsic curvature. Therefore, even small movements along the coalescence time parameter will result in automatically not accepting the hypothesis of the single effective source. For the cases of spins, we see that it's highly degenerate, with a strong degeneracy. For this case of chirp masses and spins, we see a nice curved zone that has to be cut off somewhere along here due to the fact that due to the spin degeneracy. And an interesting part is that the chirp mass and the phase, coalescence phase, has these rough edges here, like this pointy places. This is not an This is not a numerical artifact due to the fact that when we did the simulation, when we did the delta, we made sure that the angle had a lot of steps, like 500 steps in each direction. Therefore, these are not numerical artifacts. More, they say something about the geometry of the manifold in these particular directions. I'm not entirely sure what, because it's too early to make any strong claims. But the only thing that I can say with confidence is the fact that these are not numerical artifacts, as well as with the coalescence time and phase here. This is what we did till now, but we have work in progress. From the simple case that we discussed here from 2 to 1, we are going to an n plus k to n. This is a generalization of the simple case that we have talked about, and we can see right here that the general formula that the residual resembles quite well the one from the 2 to 1 case. This being, I will briefly summarize, this being actually the second fundamental form. This is the covariance matrix, and this is just like a weighted weight. Uh, this will be very soon in publication. It's almost done in preparation. The manuscript is almost done, and we will send it very soon to publication. The takeaway home message is that two nearby LISA sources can look like one when the two-source superposition lies close to the single-source manifold in the detector's noise-weighted Hilbert space. Okay, and the mathematical mechanism is the optimized remover in the optimization removes the tangent components, and the first leading component is the irreducible residual normal component, and basically the second fundamental form in M1. I have to emphasize this, that these are properties of the M1 manifold, so the single source manifold, not the two source manifold. And the general formula is this one that we have talked about. We have higher orders, but we didn't discuss them. Thank you.
All right, let's thank our speaker. Are there any questions from the in-person audience? Any online questions? Okay, well, our next speaker is coming up. I'll just ask a real quick one. When you're doing these comparisons, I think you're assuming that the sources are located in the same spot in the sky. If you move them...
No.
No?
No. Exactly. I forgot to say that. The two nearby sources, this is actually a great question. Two nearby sources doesn't mean in the sky. It means in parameter spaces.
Yep,
So
right, but you didn't list sky location as some of your parameters.
No,
That's why I was confused.
I did not.
Okay.
Sure, yeah. Yes.
Okay, let's thank our speaker again.
Thank you.
All right, next up we have Vikram Manikantan from the University of Arizona.
My name is Vikram Manikantan. I am a astronomy PhD candidate at the University of Arizona, and I'm really excited to tell you about my recent work attempting to model the multi-messenger emission from supermassive binary black holes during their late in-spiral with both eccentric and mad 3D simulations. And this is work done in collaboration with my advisor, Vasilis Paskalidis, and Gabriele Bozzola. A quick refresher for a room that I'm sure does not need it. LISA is going to be sensitive to 10 to the 5 to 7 solar mass binaries, out to redshifts with some incredible signal-to-noise ratios for the specific 10 to the 6 solar mass binary. These supermassive binary black holes are expected to be ubiquitous, forming as the product of galaxy mergers. And they're also expected to be extremely useful multi-messenger sources. During their late in-spiral, they'll emit gravitational waves, as we know. But if they're born in wet environments, as we imagine for galaxy mergers, they'll also produce electromagnetic emission across the electromagnetic spectrum from their accretion and outflows that they launch. However, understanding what these supermassive binaries might actually look like is extremely difficult, especially when coming to distinguish them from single supermassive black holes. And so to understand what they might look like, modeling of these binaries must start now so that we can maximize the scientific return from LISA when it launches. And I'll mention in just a second, but the part of the in-spiral that I care about is right here at the end of these tracks. So one issue we encounter when studying supermassive binary black holes is that their evolution spans 10 orders of magnitude in space and time. And so we start with a galaxy merger, which often sets the initial conditions for these supermassive black holes as the in-spiral. And then gas and stellar interactions on their way down to merger will help remove angular momentum until they reach this late in-spiral where gravitational waves take over. And so this is the regime that I care about and that I'll be talking about today. So when it comes to multi-wavelength and multi-messenger modeling, there are a few things we have to care about. To model the gravitational waves, we have to solve Einstein's equations. And to understand electromagnetic emission and the magnetized accretion flow, we have to solve the equations of magnetohydrodynamics. Here I am neglecting to talk about radiation, but there have been a few talks already, and I encourage you to look back at the previous session to see. That's to see the number, the session number, not what I'm telling you to do. And so to do our multi-wavelength and multi-messenger modeling, we use three-dimensional, fully generativistic magnetohydrodynamic simulations within the Einstein toolkit. And so if you're unfamiliar with how these simulations go, we generally set up our black holes in our spacetime first. In our case, we have binary black holes which are equal mass and have no spin. We set them on an orbit. The separations that I'm going to talk about today are at about 20 gravitational radii and 30 gravitational radii, which are 25 and 120 orbits from merger, respectively. And then we initialize a circumbinary disk around this binary with some initial poloidal magnetic field. Now what that looks like in practice, now we're looking at the simulation. This is an XY slice, so we're looking face down at our binary and our disk, and a vertical slice on the right of the gas density. That's the gas density on a color scale. And we see a disk as I just described. There's a magnetic field in there too that I haven't shown. And so if I turn this into a movie of our 30 GM over C squared, our 30 RG separation binary, it looks something like this. And so initially there are tidal streams that fall in from this circumbinary disk to form these mini disks around each black hole. The accretion flow at the moment is relaxing, as we like to say, which means that you shouldn't quite trust the results of what you see just yet. I'm going to let this binary evolve, and while that happens, I'm going to talk about what questions we need to be asking to actually determine electromagnetic counterparts for a system like this. So the first thing we ask is, what is the accretion rate and the periodicity? Is there a jet luminosity? Yes, and does that have a periodicity? Do the black holes host mini disks, and for how long? And how does this contribute to the thermal emission from the system? And is there any sources of non-thermal emission from the jet or magnetic reconnection from the horizons? You'll notice the simulation has got a little bit funky. I'm going to talk about this in the second half of my talk. And so in this talk, I'm going to talk about both eccentric binary black holes. I've listed my key conclusions here, and I'll come back to them. And I'll also talk about this binary at a large separation of 30 gravitational radii that develop magnetically arrested mini disks. Okay, so first, eccentric binary black holes. Here I have a movie of the simulation of a binary with 0.17 eccentricity. Again, it's a face-down slice, so an XY slice of our simulation. You're going to notice these funky units. If you're not familiar with them, there's a rough conversion you can do. Please ask me about them after if you're still a little confused. And the first question we ask for this binary is, what is its accretion rate and what's that periodicity? And so the first distinction we have for eccentric binaries from their quasi-circular counterparts is that the mass accretion rate is periodic at a fundamentally different frequency to quasi-circular binaries. So what I'm showing here is a time series or light curve of the mass accretion rate with time on the left, and on the right column is a Fourier transform or the power spectral density of that Fourier transform of that signal. And so for the top row, you have the quasi-circular binary that has a fundamental frequency of its periodicity at 1.4 times the orbital frequency, right there. And for the eccentric binary, that's fundamentally different at 1 times its orbital frequency. And this periodicity is actually driven by pericenter approach, and we're quite confident that it's unique to eccentric binaries. Okay, so now we ask, what is the jet luminosity, and does that have a periodicity? The answer is yes. And so in the top panel here, I am plotting the light curve of the jet luminosity versus time. You'll notice there's a slow rise in the jet luminosity. That's the fluid relaxing into some sort of steady state. And you'll notice with the thin black and the thick red lines, they begin to oscillate. And this is the luminosity of the binary oscillating with time. And if we do the same Fourier transform, we find that the eccentric binaries have a jet variability at exactly their orbital period. And the final question we ask about this binary is there any non-thermal emission, and can we actually determine whether there is an observable counterpart to this accretion? So we perform a radiative transfer of the jet synchrotron emission. I built a radiative transfer code to do this. Some of the assumptions are here. I'll leave them up, and please ask me about them if you have any more questions. The first thing you'll notice is that we recover the synchrotron SED quite comfortably. If this is familiar to you, then I hope you recognize it. If not, this is a very well-known shape for a synchrotron spectral energy density. There's a power law on both sides, joined by a smooth peak. But this is not yet interesting. What's interesting is when I play the movie. And when I play the movie, you'll notice that this light curve, or this SED rather, is bouncing up and down. And so what we then do is I take this spectral energy density that's frequency dependent, That's luminosity on the y-axis and frequency on the x-axis, by the way. And I integrate it in frequency, and I plot that as a light curve. We'll notice that the synchrotron luminosity from eccentric binaries is also periodic. And it's actually periodic on exactly the orbital period. You'll also notice that it's not quite sinusoidal. It's quite sharply peaked. And that's actually a characteristic that we're going to look at in some supermassive binary black hole candidates that I'm currently building an analytical model for. And finally, if I plot the amplitude of the gravitational wave strain, we'll find that the synchrotron bursts are actually completely coincident with the gravitational wave bursts. Okay, I'm gonna leave that there. And I'm gonna talk about this binary at larger relativistic separations in the last 3 minutes. So I'm gonna let this movie play. It's the same one as before. I'm actually gonna, if I can find my mouse, I'm gonna take it a little further. So, all right, it's just gonna have to play. So this is a separation of about 30 gravitational radii. That's about 100 orbits from merger. It is the longest simulation yet in full GR plus MHD. I don't know how much longer I can keep saying that for, because I'm sure it's gonna be overtaken soon. So I'm gonna get as much out of it as I can. And we're gonna ask some fundamental questions. So do the black holes host these larger mini disks that we think might exist around supermassive binary black holes at larger separations? What is the accretion rate and its periodicity? And is there non-thermal emission from the jet or magnetic reconnection near the horizons? Before I answer those questions, I have to describe magnetically arrested disks. And so a magnetically arrested disk has become quite a common end state in single black hole accretion. What magnetically arrested means is that your central black hole here is accreting gas from this torus. That gas is carrying with it magnetic field. Magnetic field actually then saturates onto the black hole. And there's so much magnetic field here that it exerts an outward force or pressure, magnetic pressure on the gas. And this begins to regulate accretion. To measure a magnetically arrested state, we often use this parameter called phi black hole. And this is an integral of the magnetic field on the horizon normalized by the mass accretion rate. So how much magnetic field is threading the black hole horizon? Phi black hole reaching a peak suggests a magnetically arrested disk. And they seem to be quite agnostic to initial conditions. And in fact, the Event Horizon Telescope have suggested that it's the best model for explaining the accretion flows around Sagittarius star and M87 star. In addition to that, magnetic reconnection can actually power flares in the infrared and X-ray within the disk. And so the question naturally becomes, can binary black holes have magnetically arrested disks? And in our work, we show that they can. Okay, so here in the top panel, again, it's an XY slice of our binary. And on the bottom, I'm plotting a time series of phi black hole. That's the black hole magnetic flux. You're going to notice it rise until it reaches a peak, at which point it falls rapidly. And when it falls rapidly, you'll notice a bubble erupt from that black hole just there. And this is going to repeat. And so mini disks are bringing magnetic flux to the horizons, and they saturate the horizons with magnetic flux. The flux erupts from the horizon and proceeds through the mini disk into the cavity. And this phi black hole is oscillating with time and with the flux eruption events. This is quite similar to single black hole accretion studies, if you're familiar with them. I built an open source diagnostic tool within the Einstein Toolkit to measure this, to measure the horizon flux. If you use the Einstein Toolkit, please use it. And if you have any questions, please ask me. I will reply to you. All right, that's really blurry, but we will keep going in the last 15 seconds. So what you'll notice here, if you squint, is that there's magnetic field threading the horizon. This is an XZ slice, so you have accretion flow here, and your magnetic field in white lines. And they're actually squeezing at the equator. And this is phi black hole at its very highest. Eventually, that magnetic field is going to reconnect, form a bundle, and that reconnection is actually going to power non-thermal flaring. And this is when the magnetic field actually drops on the horizon. And that bundle is going to buoyantly move away from the black hole, and phi black hole is going to begin to increase again. And so that act of reconnection and formation of magnetic flux bundles as a product of magnetically arrested disk is what's going to power an additional non-thermal flares from these supermassive binary black holes. And I will leave you with my conclusions, and I'm happy to take any questions.
All right, what questions do we have? Yep.
Thanks for the great talk. I was thinking that when you do this equal mass circular simulation, you do not talk about the lump feature. Is it because your domain is small or?
No, my domain is big enough to capture the lump. The lump takes some time to develop. We also see it, but it just was not the focus of the study.
Okay.
Yeah.
Okay. Thanks. And what's the aspect ratio of this?
Like 0.3, so it's like a thick disk, sub-Eddington. So like 10 to the negative 2 Eddington, we assume.
So I know for a circular black hole, it's tilt the orbital twice the frequency. Is this 1.4 a function of eccentricity, or is there some other place it comes out of?
Yeah, so the question is about where does the 1.4 times the orbital frequency arise for the mass accretion rate? And so that arises for quasi-circular binaries, and it's thought that it is the beat frequency between the binary frequency and the lump in the disk. And so I think if you do the math, those frequencies align, the lump and the binary align at about 1.4 times the orbital frequency. So that's conventional wisdom. Yeah. Yeah.
Any other, yeah.
Thank you for that talk, Vikram. I did actually want to ask about your second bullet point here. You said that you have expected flaring in infrared and X-ray bands, and in gamma ray energy ranges, there are some observations of AGN, things like that we see flares from on potentially quasi-periodic timescales. Does your model say anything about the gamma ray energy range?
No, so I personally have not done any radiative transfer of these non-thermal emissions, but previous works have modeled this in the case of like Sag star and M87 star. In terms of quasi-periodicity, we initially see some, and we think the quasi-periodicity in the flux eruptions and therefore the flaring arise from quasi-periodicity in the accretion rate, but then that dies down, and it's not clear if there is a periodicity after that.
Okay,
Yeah.
thank you.
Okay, online? No online? Is it a quick one? Okay, let's have our next speaker work his way up.
Also great talk. Regarding the MAD state, it seems like it's a regulatory process, the binary as an element. Do you ever reach a true MAD state, or does it kind of plateau at a level below, or where does it stand?
That's a really good question. And so a true MAD state, it'll take 5 seconds. This phi black hole parameter, like what it saturates to, I think is what we'll consider a true MAD state. What this parameter is, even for single black holes, is not well established for different equations of state and different accretion regimes. I don't think this will achieve a true MAD state because of the nature of the periodicity of the accretion. And so I don't think you're just able to hold as much magnetic flux onto the horizon. But the simulation is still going, and it's evolved past what I understand. And so we'll have to analyze it again and see what happens.
Let's thank our speaker. Okay, next up from just down the road is Charlie Mpetha from NASA Goddard Space Flight Center. Going to be talking about Delensing LISA standard sirens.
Okay, hi everyone. Yeah, my name is Charlie Mpetha. I'm an MPP at Goddard, just down the road. And I'm here to tell you about some research that I started during my PhD a few years ago, and I'm still just kind of wrapping up, in collaboration with Giuseppe Congedo at the University of Edinburgh. So broadly, it's on how we can use lensing of the CMB to remove the lensing effect from supermassive black hole binaries observed with LISA, and then thereby improve our cosmological constraints from these sources. So just a quick kind of refresher on standard siren cosmology. So the idea is that from our gravitational wave, we measure the amplitude and how it evolves over time, and that provides us with our distance measurement to our source. And then if we also obtain an electromagnetic counterpart, from that we can get a redshift. And so from there we have a distance redshift relationship, which allows us to probe cosmology, which you can see in these equations here. So on the right we have h naught, the present expansion rate of the universe, and omega m, which is the matter density. So these are two geometry parameters that are of interest we want to constrain, especially since H0, there's current tensions between early measurements of H0 from the CMB and nearby measurements from, for example, supernova. And so LISA is kind of an excellent, has excellent potential to addressing this tension because it observes these sources at quite high redshift. So in this kind of intermediate redshift regime between the late and the early time. And so constraints on H0 from LISA could be very valuable in addressing this H0 tension. So we need to think about how we can kind of best constrain these cosmological parameters with these sources. And so for this, we assume that these supermassive black hole binary mergers come with an electromagnetic counterpart up to some maximum redshift. So the largest source of uncertainty, especially at high redshift for these events, is actually weak lensing. So you can see the situation illustrated here. You have some binary merger at some high redshift, the merging black holes, and they travel through the universe past this large matter overdensity, for example, a galaxy cluster. And so this kappa value just tells you kind of the size of this matter overdensity. And as it passes by this lens, then the amplitude is actually increased. So it's a lensing effect. And because we infer the distance from the amplitude of the wave, this means this is going to bias our distance measurement, and so thereby biasing our cosmological parameters. So weak lensing causes this bias in our cosmology. And you can see how the form of the bias right here. And so especially, like I said, as we go to higher redshifts, this is actually the most dominant source of uncertainty. And so we can kind of mitigate this, then we can improve our constraints. And it's very important that we have a correct treatment of the impact of weak lensing, otherwise we're going to have biased results. So how can we mitigate the impact of weak lensing? The most simple approach is to just increase our uncertainty, increase our error bars. So this would be the uncertainty just coming from the waveform. And then we can add this extra uncertainty term because of our lack of knowledge of the degree of lensing that the wave has experienced. But this obviously means we lose information, and can we do any better? Is there anything better that we can do? So that's where delensing comes into play. So delensing essentially is using some external information on the matter content between the gravitational wave and us, and using that external information to remove the lensing effect from the gravitational wave. So we can see here, for example, we have our binary merger, and it travels through this matter overdensity, but we also have images of galaxies. And so the first idea of how we can perform this delensing is to measure the shapes of these background galaxies, and in the usual lensing approach, infer what the lensing field is by measuring the shape distortion of these galaxies. So that's like traditional weak lensing with galaxy surveys. But it was found recently that for this to be kind of viable, for this to provide enough information to delens the gravitational wave, you need an extremely high number density of galaxies, upwards of like greater than 1,000 galaxies per arcmin squared. And considering with JUSD and our best current surveys, we might reach a few hundred at best. This is kind of technically unfeasible, so it's too challenging with galaxy surveys. And so we still want to do delensing because we can improve our constraints, but maybe we need a different approach. And so that's where CMB delensing comes into play. So instead of this being a set of galaxies, you can imagine this is light from the CMB. Obviously the binary merger will have occurred at a closer redshift than the CMB. But because the CMB lensing kernel peaks at around redshift 2, most of the lensing information is coming from lower redshift. And so there still should be some correlation between the magnification experienced by the gravitational wave and that experienced by the CMB. So there's other kind of neat advantages of using the CMB. One is that it's nearly full sky compared to galaxy survey, which are more limited in sky area. And again, it probes these higher redshifts, so that makes it even more complementary for LISA binary mergers. These are going to be higher redshift sources. So just give a quick overview of how this CMB lensing works. So we have this animation here, which is flicking between a lensed, a lensed and unlensed CMB. So this is a kind of temperature map, and it kind of creates this small distortion of the temperature field, and then this is the residuals between these two maps. And so it induces these kind of correlations in this map. And so if you can identify these spurious correlations in your CMB map, you can infer the lensing field, and then that provides you information on the intervening matter distribution. So just to kind of summarize our approach, the analysis pipeline. So we start with these realistic supermassive black hole binary merger catalogs created by Alberto Mangiagli in 2022. So these assume different seed models for the binaries, and they have multiple realizations, so you can do like a full statistical analysis, kind of varying different properties of your catalog. We assume, or we use realistic CMB lensing reconstruction. So we start with a realistic CMB map, apply a lensing field, add realistic noise properties of a realistic CMB detector, and then reconstruct a lensing field. So the reconstruction is not perfect. And so this is kind of an example of a reconstructed map where it's quite coarse and grainy, and that's because there's some kind of maximum resolution of your reconstruction. And so we're saying, imagine a binary merger occurs somewhere on this map, and we kind of measure a value of kappa or a degree of lensing at this point. We can then map that to what we expect the gravitational waves lensing to have been. And so this is our step 3, and this is kind of there's a lot going on, under the hood here. There's a lot of work in doing this, but the idea is you can use high-resolution numerical simulations, lensing simulations, to calibrate the relationship between what's the magnification experienced by a CMB photon as it travels all the way through the universe, and of a gravitational wave as it travels from a nearby redshift. There's some relationship between those two values, and you can kind of calibrate that with your simulations with an associated uncertainty, of course. Okay, so that's kind of the full pipeline. And so I'm just going to show some plots, some contour plots, cosmology results to show the impact of our delensing procedure, just going through step by step. So in this first case, we have absolutely no lensing. So this is totally unrealistic. We've assumed that we have a supermassive black hole binary catalog, and the gravitational waves propagate through an empty universe and arrive at our detector, and we don't need to do any mitigation. And so we have very precise constraints on our cosmology because there's no lensing. So this is unrealistic. This is what happens when we have lensing. So now the lensing means that we have this bias in our distance, and so a bias in our cosmology. But again, this is unrealistic because we haven't implemented any mitigation. So we know lensing exists, so we're going to do something to correct for it. So this is the kind of bias that you can expect because of lensing. So now we've added this lensing uncertainty term that I introduced earlier. So this is the simple approach. We've just dilated our error bars, and that means our constraints are broadened. And so we've kind of mitigated this bias partially, but at the expense of information. We've kind of really severely reduced our cosmological information through this approach. And so this is not ideal. So then finally, we apply our full delensing procedure using the realistic merger catalogs and this realistic CMB reconstruction. And you can see that the bias is largely mitigated, and also the uncertainty is reduced. So it's not, really, really good, but I think this is quite a good result, and it means that we can improve our constraints on our cosmological parameters just by using this CMB information, which is already available. Will already be observed by these CMB detectors. So that's kind of the process in a nutshell. Future directions are to explore this for a range of actual realistic CMB detector properties. These results I've shown, we're using kind of an S4-like configuration, but as we know, S4 has been discontinued, so we need to maybe look at Simon's observatory and see how well that will do. And also to maybe extend this to binary neutral star merger catalogs as well. These will be lower redshift, so perhaps because they're low redshift, the matter traversed by binary neutral star merger events will be very different from that experienced by the CMB, but still there could be some information you can gain there. And so we expect to submit this in the next few months. So that's it. Just to summarize, with galaxy surveys, delensing is prohibitively difficult, but delensing with the CMB can reduce the bias and uncertainty of these LISA observed supermassive black hole binaries. Thank you.
All right, very punctual.
Hi, you described the effect of the lensing as, I think, introducing a bias. Does it always increase the apparent luminosity, or does it sometimes decrease it?
It can decrease as well, definitely. So if it goes by an overdensity, then it will appear closer, and underdensity, it will appear further away. So your magnification probability distribution, or your lensing probability distribution, has some shape, and the mean is often around 1, but obviously it can have positive or negative values. And that's something you can kind of calibrating your simulations and your analytic predictions for lensing.
Thanks.
Thanks for meeting me halfway.
So thank you very much. This is very interesting. There is one thing I didn't understand. I suppose that the CMB allows you to find the lensing pattern with a given resolution on the sky, right? Although the binaries probably resolve much better. So how can you reconcile these two things? You understand the question?
Yeah. So essentially, there's a resolution limitation in the CMB map, essentially. Yeah. So that's kind of the largest. That's why. That's partly why this delensing procedure is not perfect. So there's an uncertainty term essentially. So using these high resolution simulations, then you can kind of look at a single small, essentially a point source, and say what's the magnification of this point source. That can have a wide range of values. When you do your CMB reconstruction, then you're essentially smoothing over this map. And so there is an offset there, but we fully take that into account. So there can be a bias in your recovered value from your CMB reconstruction in the sense that it's not a perfect reconstruction. And also there is an uncertainty in that there can be a large range of values from your reconstruction. Yeah.
Any other questions in the room? Questions online? Okay, I've got one. When producing the catalogs, we have to do something. This seems like a perfectly good thing to do. If I went to a conference that was all about delensing things that are at high redshifts, how controversial would this idea be, and how big of an argument would we start if we said we're going to take this way to go?
How controversial? Yeah. In what sense?
Hold on, your alarm was going off. In the field that worries about delensing, is this approach? Do you start arguments when you talk to your peers about going this way? And do people have strong feelings about different ways to do delensing?
I would say this is a relatively unexplored field. I think the largest kind of complaint would probably be, as was the question earlier, the resolution of the CMB reconstruction. And since we're kind of forecasting future CMB detectors, obviously this hasn't been proved in practice. So that'd probably be the largest source of contention. But we're using simple assumptions on like the noise properties of these detectors, on how well they can reconstruct the map. And so I think it's realistic, but I think that would probably be the largest question of how well would the CMB reconstruction actually do.
Okay. All right, let's thank our speaker. Next up, we have Cordell Harris from the University of Michigan and some slide gymnastics.
Okay, so I have a multi-messenger approach to constraining the hardening timescales of supermassive black hole binaries. And I'm going to start on the gravitational wave side of things and move into the EM part. So I look at supermassive black hole binaries, and that's going to have some overlap with LISA stuff. But first, let's talk about pulsar timing arrays. So the pulsar timing array is a collection of observed pulsars with their time of arrivals of their pulses. And if you have a gravitational wave come through, that's going to mess up the time of arrivals. There's some other stuff that will do that as well, but gravitational waves will definitely do that. And the plot I have here is the correlation strength of these differences based on the separation angle of the pulsars in the sky. And so the black dashed line is what you would expect from any gravitational wave background, whether that be from supermassive black hole binaries or cosmological sources. But the blue points are what Nanograv, the American pulsar timing array, measured, and you can see that it fits the line. So for the rest of this talk, we're going to assume this is caused by a population of SVHBs. So we can construct a population model to explain this if we go through and kind of think about the astrophysics of where these systems come from. So first, we're going to put together a population of galaxies by looking at a galaxy stellar mass function, for example. So how many galaxies at each mass bin do you have? You can put that together with a galaxy pair fraction. That's something that you observe to get a number of galaxy pairs. And then you can figure out how many actual merger remnants you should have at a given redshift if you throw in a galaxy merger timescale. So combining those, we get a galaxy merger number density. We can import a black hole mass scaling relation, so just the mass of the black hole is correlated with the bulge mass of the galaxy. You can involve that with the galaxy stellar mass function and add in all that stuff we talked about before, and you can get a pair number density for black holes. So now across cosmic time, you know where your black hole pairs start. But that doesn't tell you anything about the gravitational wave information because you haven't involved them yet. So you need a pair hardening rate. And that's gonna get messy because as we saw, there's decades of separation that the black holes have to go through with a bunch of different physical processes involved. But if you get this, you get a gravitational wave frequency number density, which is what we can think of as a gravitational wave spectrum. And so that's what you see with these violin plots here is the inferred gravitational wave background from PTAs. Okay, so the hardening timescale, very uncertain. We have some constraints from gravitational waves, but can we add EM constraints? And I'm gonna tell you the answer is yes, otherwise I wouldn't be here. So there are electromagnetic observables that we can use as tools, and so I'm gonna have a little schematic here where we have timescale on the y-axis and separation on the x. So the first thing that happens is dynamical friction. So after the galaxies merge, you have drag from the background density, and dual AGN live here. They can act as probes for that. In about parsec scale separations, you get core galaxies, and you can have binary AGN, which we have like one example of, so that's cool. And then last stage, gravitational waves. I'm gonna focus in on this middle panel here where we have core galaxies. So what are core galaxies? Core galaxies are massive early type galaxies, and they are identified by their surface brightness profiles. Specifically, you get a flattening in the inner region. So this is a real galaxy, NGC 1399, and this is its surface brightness profile with the data points being red. There's also a blue curve that sits above that in the inner region, and this is the signature. So if you extrapolate the surface brightness profile from the outer regions and it overshoots the actual measurements, that's a core galaxy. So it turns out that if you model these with n-body scattering experiments, with SBHBs coming in through a density of stars, you can reproduce the observed core structure and a lot of the kinematics involved in these systems. And so I'm just showing you on the left, that's observed data, and on the right, that's a simulation. Okay, so we have gravitational wave background that can tell us about things. We have core galaxies that can inform the stellar scattering, that center regime. So what I did was I developed a program that can specifically use properties of core galaxies to look at what the supermassive black hole binary population should be doing. So I mimicked the thing that I showed before, so I'll run through it real quick. But instead of doing these stellar mass functions and stuff, I'll just use cosmological simulations and merger trees. I'll import a black hole mass scaling relation. I'm gonna make my own hardening prescription. And instead of comparing to the characteristic strain spectrum, I'm gonna look at the mass deficit scaling relation. So what is a mass deficit? So remember that profile where you had the extrapolated thing that overshot the inner region? Well, here's another galaxy, M87, and the blue is the observed surface brightness profile. It's a model, but that's fine. And then the purple is an extrapolation. And the gray region is gonna be a luminosity deficit since the brightness of galaxies is correlated with their stellar populations. For every galaxy in my sample of 116 local core galaxies, each of those has a mass to light ratio that you can apply to this to turn it into a straight mass deficit. So the plot on the right-hand side has log of the stellar mass deficit versus stellar mass for a bunch of different galaxies. All right, so there's the observed data. For the simulated, I used illustrious TNG and its merger histories, and I had to use some post-processing because core sizes are pretty small, astronomically speaking. They're less than about half of a kiloparsec. There are large ones that are more than a kiloparsec, but there's that. So for the central regions, I did a bulge component, a dark component that's just an NFW, and then for the scaling relation, I'm just gonna import the Corminian-Hoe relation, and that can be changed later. Okay, into the hardening prescription. So I'm going to assume circular orbits and that all mechanisms are involved. It's just a superposition of dynamical friction, stellar scattering, and gravitational waves. For the dynamical friction part, I'm just going to take what Chandrasekhar gave us all that time ago, and then gravitational waves, we understand those. So those are set for me. It's this middle region, the stellar scattering, that's going to play a key role here. So this is going to happen at parsec scales, and the orange thing I have here is actually A dot, and the thing to pay attention to is that there's the dimensionless hardening parameter H that sets how fast the binary is evolving, and I have H hat in there, which is an efficiency parameter. The purple is the mass ejection, which depends on the dimensionless mass ejection rate, J, which is inversely proportional to the hardening rate. So there's going to be some effects that happen if you change the efficiency of the stellar scattering. And so I'll walk through that really quick with this panel. So if we decrease the efficiency of hardening in this regime, then of course the speed, A dot, goes down, the time to coalescence goes up, but also the mass ejected goes up. Then notice that the transition point where stellar scattering enters into the gravitational wave-dominated regime, that actually moves to further separations. So the frequency of gravitational waves that start to dominate goes down. Alternatively, we can increase the efficiency, increasing the rate, and then the time to coalesce goes down. Mass ejection goes down as well, and then you see that you enter into the gravitational wave-dominated regime at closer separations. So I can find the optimal efficiency then if I go ahead and compute the mass ejection for all of these simulated galaxies and compare it to what I have for the observed galaxies. So I'm going to go ahead and take away some of the color and error bars there so we can see what's going on. On the panel on the right, I have log of H hat just because it's easier to see this way, but there's a bunch of different values that I can test out. So if I try something that's really small, you can see that the predicted mass deficit stellar mass relation is too high. Then I can choose something that's more efficient, but then it's too low. So of course it's going to be somewhere in the middle. If I go ahead and do the optimization, I find that H hat is 1.6 something, which is greater than 1, which means that hardening rates are faster than the fiducial prescription in my model, which is consistent with there's something else that's going on that the model isn't capturing. There's additional mechanisms to explore. But I do find a max likelihood rate of like 1.4 gigayears, which is consistent with what like gravitational wave background stuff is looking at and all that stuff. Okay, so we can actually swap these prescriptions to see if they're consistent with each other, EM and gravitational wave. So if I do that and plot the median hardening rates, you can see that for core galaxies, the hardening rate in total, it takes a lot longer for the binaries to coalesce. And it's specifically affecting in the stellar scattering regime, which, as we saw, had impacts on the gravitational wave background. So if you look at what the core galaxies say, you don't get kind of this turnover in the low frequency regime that the gravitational wave background models say should be there, right? And then you don't predict the amount of mass deficit you observe, though, if you use the hardening rates that the gravitational wave background analysis infers, right? So there's some tension here. But there are some ways that we can get around this. One is that this model was circular orbits only, and we know that when black hole binaries form, they probably do so with high initial eccentricities, which make the binaries evolve faster, and so you would eject less mass. You can have core enhancement from SBH recoil, so after they coalesce, the remnant can be kind of ejected from the nucleus, not out of the galaxy, return and kind of puff up that core. That makes coupling the hardening rates with mass deficits difficult. But that's a promising area to look at and very interesting for other types of gravitational wave analyses. And gas dynamics may play a role in some of these, and I know these are early type gas-poor galaxies, but they came from gas-rich mergers in the past, so who knows, right? Okay, So what can I do with this? This is very preliminary. I've got a couple projects I'm working on. One of these is if you look at this kind of waterfall plot for the sensitivity of different gravitational wave missions, you can see that there's this small overlap between the nanograv and international PTA and the LISA mission. And so if I go back and I look at, for the best fit model, what are the binaries that are kind of in this regime? What are they doing? Where are they? I can kind of look at that. But this is very preliminary. We can talk about it later. The other thing I'm looking at is using the properties of host galaxies at z=0 for the local core population. I'm trying to see if I can get a handle on odds estimation for whether or not there's a binary there now, like at z=0. And so I've added some cool bells and whistles to my model to be able to look at binaries. And you can see in the color bar here that some of them do show up, some of them are binaries, and there's a distribution of separations. I also make a distinction between binary and dual, dual being not gravitationally bound, right? Okay, so I'll just leave my summary here. So I developed a multi-messenger thing, compared some stuff, and we'll see where that goes in the future.
Okay, we got a question already.
Okay, so this analysis assumes the hardening rate to be a constant, to be a free parameter, and you feed it a value of 1.6 something. So my question is, how do we reconcile this value with the scattering experiment results from Cezanne or Quinlan of 15 to 20?
Yeah. So that's a good question, and this is something I kind of glossed over. But the hardening rates, H and J, they are actually just fits from the Cezanne et al. 2006. And then I just add an efficiency parameter to modulate that, and it's not affecting like the shape of the distribution of ejected stars or anything. It's just changing its amplitude. And so what the model is saying is if you have more efficient hardening in this regime, that energy is not going to stars, it's going somewhere else. So the hardening rates themselves are the same. This is basically just taking some of that energy away and putting it somewhere else. Does that make sense? That's the question. Is it because of eccentric binaries that this model isn't working, or is there gas drag that's kind of changing things? That's the question.
Online? Okay, we're going to keep going because we want to stay remotely on time. Next up, let's thank our speaker again. Thank you. And next up, we have Nina Kunert from the Observatoire de la Côte d'Azur.
Yeah, hello everyone. From my side, my name is Nina Kunert. I'm working at the Observatory de la Côte d'Azur in Nice in France, and today I will talk about joint multi-messenger inference of double white dwarfs. So this is a work started together with Alexander Criswell and Astrid Lamberts. So let me set the stage by just shortly reminding that double white dwarfs will be the dominant source class for LISA, with millions of these binaries being located across the galaxy. And yeah, so the majority of these systems will form the foreground, but a subset, and the estimate is around 10,000 sources, will be resolvable. And another interesting subset are these verification binaries that you can see here on the right-hand side in the plot. So these are electromagnetically known systems and guaranteed sources for LISA detection. And another important thing also to mention is that these are ideal candidates for multi-messenger astrophysics. So as you can see, I highlighted one specific verification binary here in the black box. And this is sort of a vanilla case, and also makes sense, of course, to perform multi-messenger inference on this system. So if you are not really familiar with the actual observation. So this was an observation done in 2019 by Kevin Birch and collaborators. And you can see here two components. So from the gravitational wave side, you can see here that an orbital decay has been detected and confirmed you can see this by checking out the eclipse arrival time deviation here, shown on the left-hand side in the plot. And so this orbital decay is consistent with the gravitational wave in spiral. Now, for the electromagnetic side, you can see here on the right-hand side plot the actual light curve that has been measured. And you can see, for example, a deep primary eclipse happening every 7 minutes and a more shallow secondary eclipse, and also some pretty outstanding out-of-eclipse modulations of the light curve. And this is mainly driven by these two components in this binary system. So here we have a hot primary with a mass of 0.6 solar masses, and it's likely a carbon-oxygen white dwarf, while the secondary is cooler and is likely a helium core white dwarf. So, and this actually is a pretty interesting source also for performing the multi-messenger inference in the end. But for now, I would also like to shortly go over what has been done in the past. So you can see here work from 2022 from Johnson and collaborators, and they performed a sequential multi-messenger inference that you can also see here in the middle illustration. So as you can see, there's a lot of different steps going in there to actually arrive at the combined estimate. But the main idea or the main message I want to convey over here is shown here on the left-hand side. So you use one messenger first, let's say the gravitational wave part, you perform your sampling, get a multidimensional posterior out of that, and compress this then into a 1D marginal so that you can provide this as a prior for the second messenger inference. But if you do this, then you have the problem that you drop the cross correlations of the parameters. And this is actually now setting the stage for the joint likelihood approach that I'm presenting here in this work. So the idea is basically to run a joint likelihood over a shared physical parameter vector. And now the exercise or the to-do over here is to think about, okay, what does the gravitational wave part probe, but also what does the electromagnetic side probe? So for example, for the gravitational wave part, we know the amplitude, frequency, sky position, while for the EM part, it probes the eclipse pattern, temperatures, stellar sizes, and also the orbital clock. And as examples, I'm listing down here, so what is actually shared. So of course the orbital clock, the inclination angle, but also the masses, which enter as chirp mass, or the gravitational wave part is more sensitive to the chirp mass, and the electromagnetic side to the mass ratio. So right now, I want to also give you some details what's actually folded into the whole joint likelihood multi-messenger inference. So I'm just going over this shortly. So we are using the gravitational waveform model GBGBU. And for the noise, we assume an analytical instrumental noise model for both LISA TDI channels A and E, and the usual Gaussian likelihood. And for the parameter estimation, we use nested sampling. This is not just for the gravitational wave inference, but then, of course, also for the joint likelihood multi-messenger inference. And here on the next slide, you can see the simulated light curve for this specific ZTF binary that I was talking about initially. And you can see that the light curve is including different physical contributions. So, of course, the eclipse physics, but also the additional out-of-eclipse modulations. So these are these three panels below there. And you can see by checking out the numbers that for this specific binary, the reflection part is also a strong contributor to the overall flux. So with that in hand, we can go to the next slide here. I'm also listing some additional details of the electromagnetic model parameter vector. So apart from additional nuisance terms, the model is of course sampling the period, the timing, and the inclination, and also the temperatures and the chirp mass and the mass ratio. Now, why do these appear actually here? Because we use mass radius relations that are actually already folded into this electromagnetic model. And as you can see here, we're just assuming one simple mass radius relation, the Naumburg relation. This is not that tailored to this specific ZTF binary, but as a starting point to build up the whole code and code framework, it's a starting point, let's say. And for the likelihood, we also assume Gaussian likelihood with additional folding in a photometric noise, but also a model systematic term, as you can see. So this plot on the next slide is intended to give you an overview of what has been actually simulated. So everything is simulated. There's no real data folded in here for this specific binary. And as you can see, both the gravitational wave signal and the electromagnetic light curve are evolved over a time frame of 1 year. Whereas for the electromagnetic part, I need to be more precise because as you can see here, we have 12 electromagnetic windows in which the actual observation is modeled. With each of these electromagnetic windows, we simulated 10 orbits with a cadence of 10 seconds. Now coming to the results, of course, we were interested in comparing the joint likelihood approach to the sequential approach that we also saw initially. And as you can see here, this joint inference result shown in the orange, in orange color is pretty decently recovering the injected value, first of all, which is also the case for the other ones. But as you can see here, also that performing the sequential approach is also, for example, when you check out the left plot, the direction of how you actually perform the sequential approach makes also a difference. So on the left-hand side, the electromagnetic inference was performed first and then the gravitational wave one. And as you can see, you lose here the correlations from the EM part. And that's why you will have a much broader posterior in the end, shown in purple. While on the other hand, if you perform the GW part first and then the electromagnetic one, you lose somewhat of the precision for the luminosity distance, as you can see here in the right plot. So another result that I want to share is here the inference of the component masses for this binary. And so you can see here in the table that the chirp mass is pretty decently recovered and measured with a time frame of 1 year. And of course, if we increase the baseline to 4 years, the precision increases. And so the baseline, of course, makes the main difference over here, but also mentioning again that the frequency drift along with the eclipse geometry with the folded in mass radius relation is really what breaks the chirp mass and mass ratio degeneracy over here. Of course, this cannot be compared apples to the actual discovery paper of that from Kevin Birch, but so because we use different mass radius relations and there's also no tidal contribution considered here in the multi-messenger inference, and there's also no real observed data used, but as a starting point, this can show that a pretty precise chirp mass measurement is, can be expected. Now, for the conclusion, so where does this go next? So We have a starting point for a joint likelihood multi-messenger inference in which all of these physical parameters are still linked and the correlations are being preserved. And of course, this should not be done just for one verification binary, but for all of them. And for that, we are also planning to include more stellar physics, so more mass-radius relations, also the tidal contribution, and also, of course, in the future, real observed data, so that we can make use out of that. And of course, this is intended to be as fast as possible from the code perspective, though, so that we can potentially use this for a population-level multi-messenger inference. Thank you for your attention.
All right, any questions? I have a question. So you had to choose a mass radius relationship. Are there data-driven ways to just fold other observations in to infer mass radius relationship, or is that really something that you have to put in by hand?
First of all, you need to basically program that into the overall code, but a thing that I'm also thinking about is if you have a set of these mass radius relations, you can also compute in the end, you can rerun the joint inference and also get a Bayes factor in the end out of that. So you can really see what is the preference from your data. So this is a pretty cool thing. So you can also check if there's a preference for a certain mass radius relation.
Any other questions? Questions online? Okay, let's thank Nina again. And before our last presentation of the day, we have breaking news. The revised bus schedule for tonight is as follows. The buses will begin running to the Hotel Maryland and Cambria at 6:45 p.m. with the last departure from the Stamp Union at 7:45 p.m. So if you're staying here and you're counting on the bus, you can get out of here between 6:45 and 7:45 p.m. or else you got to just figure it out. All right? And with that, we have one final talk for the session. This will be Joheen Chakraborty from Massachusetts Institute of Technology, I've heard of it, who's going to talk more about these white dwarf binaries.
Hi everyone, I'm Joheen. I'm a grad student at MIT. I mostly work actually on electromagnetic counterparts of MREs via quasi-periodic eruptions, but today I'm excited to tell you about something slightly different from that, which is what we can learn about LISA Galactic binaries from electromagnetic ground-based surveys. So as we just saw in the very nice talk by Nina before me, electromagnetic surveys have already been finding LISA sources, these galactic binaries with periods of below an hour. And pictured here is ZTF from the mountaintop of Palomar Observatory. ZTF has been the single most prolific discovery channel for finding these galactic binaries, although there are plenty of other surveys. And for the uninitiated, the way this discovery chain usually goes is that some all-sky survey will take many, many observations of the night sky over years. This will give you, of order, a couple billion light curves and time series photometry that look like this, which is to say, not particularly remarkable, mostly looks like noise around some constant baseline. But then if you solve the hard computational problem of period searching and phase folding all 2 billion of these, you'll find some small fraction of them which show this coherent modulations, these coherent periodic modulations, in this particular case on a 7.95 minute period. And this is suggestive enough that when you get targeted follow-up of these sources with high cadence photometry and optical spectroscopy, you can confirm some fraction of them as ultra-compact binaries. In this case, this happens to be an AM-CVN binary. That's an ultra-compact binary with an accretion disk. And at a 7.9 minute period, that's the shortest binary known that hosts an accretion disk. So this and a couple of other sources we reported in this recent paper from about 1.5 years ago. And we're not the first ones to find ultra-compact binaries this way. It's a bit of a cottage industry by now. But before I go towards the population level science that we can start to do with these, let me just walk through some of the interesting single source or couple source science that we can do. I think one of the most interesting measurements that we can make is via long-term timing of these sources. So because they have these stable orbital periods, they present periodic or almost periodic flux modulations driven by the orbital variability. And they're really good clocks because the orbits are stable. But they're not perfect clocks, and over time their orbits decay, as we know from gravitational wave emission. And by monitoring them over long enough timescales, you can use the O-C technique, which I have a schematic of here. The O-C technique works by looking for a long-term accumulation of phase drift from the kind of compound interest that you get of small period deviations that accumulate over each passing period. And if you subtract the kind of difference between the observed timings and the predicted from a constant period model, you get, for a constant p dot, a quadratic accumulation of phase drift. So most famously, this was used to detect the gravitational wave decay of the Hals-Taylor pulsar. But you can repeat the same exercise for any system whose period is varying over long time scales. And that's exactly what we did here. If you look at the left panel, you can actually, if you look closely enough, you can even see by eye that the phase drift kind of occurs over these long time scales. And we get the same kind of concave down parabola indicating a constant in spiral with a p dot. If you look on the right and you look really closely, you'll see that it's a concave up parabola instead. And that's not a fluke, that really does happen. It indicates an out spiral in the system, a steadily increasing period. And this happens because these systems are not just pure binaries in a vacuum, right? They're so compact that the secondaries, despite being these really dense degenerate white dwarfs, can begin to overflow their Roche lobes. And the action of this is to counteract the angular momentum loss driven by gravitational wave emission. If you kind of think about the orbital angular momentum equation and how it relates to component masses and the period, and you take its time derivative, you can kind of get a quantitative feel for this argument, which is that as accreted material moves inward towards the accretor and loses its angular momentum, the system as a whole, which tries to conserve angular momentum, tries to expand in response to this. And there are a handful of systems, about 10 now, I think, for which we've been able to make these p-dot measurements. And so the long-term fate of these ultra-compact binaries is kind of to slowly in-spiral in due to gravitational wave emission. Eventually, as the donor starts to overflow its Roche lobe, the mass transfer ensues, and kind of very rapidly, within 10 to the 3 or 10 to the 4 year timescales, these systems reach a period minimum, stall their in-spiral, and start to kind of spend the rest of their life on this smooth, long-lived, slow out spiral as AM-CVN systems. And this story of reaching a period minimum and turning around, it's totally uncertain in what fraction of systems this actually happens, as opposed to the system being driven towards a merger and maybe resulting in some zoo of explosions and white dwarf merger remnants. You can turn this picture around and say, if I measure a p and a p dot, and I know something about what m dot should be based on stellar physics, I ought to be able to measure the component masses. And that's exactly what we did in this paper. We laid out some arguments that allow you to parameterize the stellar evolution to make M1 and M2 estimates based solely on the measurement of a p and a p dot. And so those contours are shown here. The nice thing about this is that these are kind of complementary to the LISA chirp mass contours, which will give you this kind of banana-shaped slope. So you can combine these kind of multi-messenger constraints for very precise constraints on the component masses. But just with the existing mass constraints that we've already made, you can estimate that these are going to be high SNR LISA sources. And so they kind of join this population of something like tens of individually resolvable galactic binaries or verification binaries that we know of already. Okay, so much for single source or couple source science, where we now know of a population of close to 100 ultra-compact binaries. So it's high time that we start thinking about what we can learn from them at the population level. And These are just the ones that I was able to rattle off upon sitting down to make these slides. I'm sure you can think of more if you try hard. But there are many questions, particularly related to binary stellar evolution, that can only really be addressed with population studies, such as what is the actual formation rate of ultra-compact binaries, what fraction of them merge, what is their contribution to the type 1a supernova rate, how many of these sources will be individually resolvable, what is their contribution to the unresolved LISA foreground, what binary evolution parameters can we begin to constrain with electromagnetic surveys, and so on. The problem with these population-level inference, so far at least, has been the extreme heterogeneity of the electromagnetic properties of these sources. If you looked closely at the earlier slides, you will have noticed that the two light curves of these couple systems that I presented earlier look quite different from each other. And here are yet two more which look totally different even from those. And the reason this happens is because binary evolution gives you a lot of phase space and different parameters to kind of play with. I have some toy animations showing kind of how some of this diversity can emerge. In some fraction of systems, the orbits are so compact that the accretion stream has no space to circularize into a disk. The separation of the two components is just a few times their summed radii. So the accretion stream will directly impact onto the accretor, and it gives you this quasi-sinusoidal waveform, like the one we saw here. On the other hand, in some fraction of the systems, this disk is able to form, and we get kind of a totally different eclipse-like morphology as the donor passes in front of the disk. And of course, you can explode this parameter space by also considering sources which aren't mass transferring at all. Suppose we have two systems which are, two stars which are detached but eclipsing, and you get something like at the bottom left. And then if you turn down the inclination so that the system is no longer eclipsing, the contribution of ellipsoidal modulations due to tidal deformation of the donor begins to dominate. And you can quickly imagine how this proliferates into a huge zoo of different classes of electromagnetic variability that can arise from these double white dwarf or ultra-compact binaries. So by my counting, the zoo can be parameterized with at least 11 different variables, such as the orbital period and the properties of the donor and the accretor, and their temperatures, as well as observational properties like their position on the sky and their apparent magnitude. And these are all going to affect how easily we can detect these systems. I've shown just a menagerie of some of the different types of light curves that we can get from these models. But the nice thing is that we can model this variability given, the primary and secondary masses, radii, and effective temperatures. And so you can immediately imagine a pipeline where if I have some population synthesis model and I would like to study the properties electromagnetically of a whole galaxy of these systems, I can model the resulting population of ultracompacts, forward model their light curves, and inject them into ZTF to assess whether I would have been sensitive to it and would have recovered it. And you can begin to take this as a first step towards trying to reconcile these galaxy-wide population synthesis models with the observations that we actually have for experimental verification. And so some preliminary results of this analysis, these are kind of exactly what you would intuitively expect, which is to first order, the most important factors setting the detectability of these ultracompacts are the orbital period. Shorter period systems are easier to detect, as well as their apparent magnitude. Brighter systems will have better photometry and thus be easier to detect. And also the inclination. For these fainter systems, which is to say most of them, the only hope we ever have of detecting them is if they're close to edge on and thus eclipsing. Whereas for the brighter systems, you have kind of this wide parameter space of inclinations where you might have some better hope of detecting them. And there's non-trivial coupling between these variables too. So feel free to ask me about that if you're curious. So now the great hope of this project is to start taking every population synthesis model of the LISA Galactic foreground that has ever been run and start running through these pipelines to start seeing how consistent they actually are with the ground-based optical data that we already have from electromagnetic surveys. So if you are a person who runs these models, please come talk to me. That's all I got.
Are you aware of the LISA Consortium's project to collect and homogenize a bunch of different population synthesis simulations of the galaxy?
No.
Let me tell you about a LISA Consortium project to homogenize and collect a bunch of different population synthesis simulations of the galaxy to do things like compare what the foregrounds will look like, what the number of detectable. So there is soon to be a probably more than you would like collection of LISA Consortium blessed pop synth models that you can run directly through this pipeline.
That sounds amazing. Thanks.
Yeah. Shane, what else did you want to ask? Any questions from the room? Any questions online? Congratulations, you've survived the first day of the LISA Symposium. Remember that the buses are running from 6:45 p.m. until 7:45 p.m. back to the hotels. The reception is now upstairs. And let's give a big round of applause to all of our speakers this session. It was delightful. Thank you.